So for this video, we're going to go back to the equation that was derived in the previous video and talk about kind of its meaning in physics. It is known as the Impulse-Momentum Theorem, and it can help us describe, again, interactions between objects where forces are exerted, just in a different frame of reference, respect to time instead of distance or acceleration. And so the idea behind a lot of things in this unit is that the amount of time that things spend in contact is relatively small. And so that's kind of the realm that we're going to exist in. So the impulse momentum theorem states the following. When a net average force acts on an object during a time interval, the impulse of this force is equal to the object's change in momentum. So the impulse is essentially defined as a change in momentum. So it's a force exerted over a time, but it's really like the point of calling it an impulse is so that we can say this is the thing that is a change in momentum. And so that equation is going to be the net average force times time equals mass times change in velocity. Now, a note about this equation, our net force and change in velocity are vectors. These two vectors point in the same direction. Now, that's going to be really confusing because change in velocity is final minus initial, and the initial and final velocity might not actually be pointing in the same direction. So what I mean to say is the direction of the net force tells you the direction in which the velocity changes. So if it's like, we'll say this out of context, if it's a negative net force, then there's going to be a negative change in velocity. And so that's what that means. Just to kind of review what we have here, the left-hand side of the equation represents impulse. The right-hand side represents change in momentum. So this is the equation that you're going to use in the first part of the unit to analyze interactions between objects, where you're just focusing on one object at a time. Now, for kind of completeness, this net force times time is impulse. If I take delta V and turn it into final minus initial velocity, I can write the following. So, in the energy unit, there were equations that had a lot of variables and equations that had not a lot of variables. So if you're looking for an equation that has all the possible variables when there's a force exerted, this is one of them. Net force times time equals mv minus mv naught, where mv is the final momentum and mv naught is the initial momentum. I'm just going to write that here. This is the final momentum. This is the initial momentum. Just a very quick aside, momentum was actually how Newton framed his second law. It wasn't net force equals mass times acceleration. It was net force equals a change in momentum over time. And so this is like the original Newton's second law having to do with momentum. So momentum was thoroughly a Newton concept, whereas energy wasn't. So there we go. So we're going to do one example problem together. It's about tennis. I never made the tennis team in high school, so I get to write problems about it and relive that all along. A tennis ball moves toward you at 20 meters per second. You swing your racket and deliver an average force of 550 newtons. If the ball leaves your racket at 40 meters per second, for how long were the ball and racket in contact? So a picture is very important, and you know how good I am at drawing pictures. So let's see what we have. This is the racket. And it's going to get swung forward. Now it's going to be moving in that direction. And that's important. So as I said at the beginning of the previous video, everything's a vector in this unit, whereas everything was a scalar in the energy unit. So to say like 20 meters per second towards you means initially the ball is moving in that direction with a speed of 20 meters per second. Once you hit the ball, right, it like squashes up against your racket and bounces off. It's now moving at 40 meters per second. Well, the point of using a tennis racket is so you change the direction of the tennis ball in a way that's favorable for you. You have to get the ball over the net, And so when all is said and done, the ball is now moving away from you at 40 meters per second. Now, momentum involves velocity. And so it's now up to you to decide the direction of each thing. And so I recommend you draw a picture, and in your picture, choose the positive direction. The positive direction for me is going to be the direction in which I'm swinging the racket. And what that means is the 20 is now going to be a negative number, and the 40 is now going to be a positive number. So you will quite often be given speeds in the problem, 20 and 40, and you'll have to turn them into velocities by picking a direction to be positive. And that's like a lot of the initial trouble with this unit is that question. So net force times time equals, now I have like my options up here. Sometimes I can do m delta v if I want to, other times I can do this. It's kind of up to you. And I'm going to show you the way that involves all the variables, but I would encourage you to think about how you could just kind of plug in a change in velocity. So I'm going to write the equation out like that. So the question is how much time the ball and racket are in contact. So that is actually equal to the amount of time that the force spends acting on the ball. So we have the change in momentum divided by the net force. So we are going to say that the net force is 550. It's not exactly 550, but it's so close, like the force of gravity is so small, air resistance is so small that the force really is almost exactly 550 newtons, so we're going to use it like that. So this means that the time it spends is the mass times the change in velocity. So one thing that I didn't do here, this mv minus mv naught, there's even another way to write this, and that is m times v minus v naught. So there's like lots of flexibility in this equation, and I would encourage you to ask questions about it if you're confused, or play with it if you are not confused. So v minus v naught, the final velocity was positive 40. Oops. And the initial velocity was negative 20. So it's 40 minus negative 20 for a total change in velocity of positive 60 meters per second. And then the net force was 550 newtons. Okay, so I calculate 0.055 times 40 plus 20, all that divided by 550, and I get 0.006 seconds. So 6/1000ths of a second. I think that's kind of reasonable for a tennis shot, but don't quote me on that, even though it's on video. I don't know that these numbers are accurate. I know the mass of a tennis ball is about that, but I don't know about the forces and the velocities. So I'm sure depending on how old the tennis player is and how skilled they are, these numbers can be very different. But I think like 0.003 of a second is a reasonable amount of time for a collision between a tennis racket and a tennis ball. So that's one example, and so you'll be working on some examples in class. Thanks.